Hello. Our next speaker is Professor Henryk Iwaniec from Rutgers University, and his title is Spectral Theory of Automorphic Forms and Analytic Number Theory.
I'm very grateful for the invitation to speak to this conference. And on behalf of Analytic Number Theory, I would like to also express my appreciation for being part of this huge construction, the elephant. I don't know which part we are given. They're probably far away from the brain, as we are not, as we are not supposed to be conceptual. Well, we shall see. So the automorphic forms occupy a large area of mathematics, which we shall visit today during this conference, many of these areas. And first of all, they provide a very solid structure for the whole number theory. Today, the modularity of L functions, the keyword, or arithmetic, number fields, modularity of L functions, and anything like that. However, I will not speak on L functions. Bill Duke will speak on L functions, automorphic functions, on Friday. He gives an account of L functions from analytic perspective. And today I will focus on spectral aspects of automorphic forms. And if time permits, I give some applications to problems in number theory. For me, the automorphic forms are really tools and provide very strong tools for cracking problems rather than for setting structures and the language in which we express mathematical structures, relations, etc. So far, there is no direct, I emphasize direct, use of automorphic functions and forms to problems, to classical problems of analytic number theory, of automorphic forms of high rank. So I will really focus on automorphic forms, mostly on GL2 forms, the functions that live on upper half plane. H is the upper half plane. In standard notation, the variable is denoted by z, equals x plus iy, x real, y positive real. And of course, I don't mean there is nothing from the higher rank group theory. There is indirect benefit of the theory of automorphic forms on GLN, and by way of improving our knowledge of GL2 theory itself. And I shall mention a few of these on some occasions. We actually heard already from Shahidi lecture how the progress in GLN, particularly about symmetric parallel functions, influenced some of our works in analytic number theory, and I will give some concrete applications at the very end of the lecture. Yeah. Maybe I should say in general terms a few words what kind of tools really automorphic forms offer us in analytic number theory. A great deal of method ideas in analytic number theory goes through formulas, identities, which connects various quantities. And there are two types of identities, I would say. One is of combinatorial type, which is very useful, in particular in the context of sieve theory. It is very useful for studying distribution of prime numbers. As I, at the end of the lecture, connect things with prime numbers, that would be the link, the combinatorial identities, and I make a statement why the combination of other things that I'll be talking about need to be combined with some combinatorial identities. Well, roughly speaking, because there is no universal harmonic analysis to treat all the objects in the world. Some are better treated by different means. And if you just don't separate these objects, you'll be really doing well in one corner and doing bad in the other. So you really have to separate that, and that's what combinatorial identities really are used for. The other type of identities are analytic type, and which are derived by harmonic analysis. Magnification, amplification, yeah, that will be the subject of talk by Bill Duke. Yeah, okay, thanks. Well, it will be too late, I think. Okay, yeah. Anyway, so the other type of formulas, identities, are of analytic type. They are derived by harmonic analysis. And example of the first, as I said, were identities in sieve theory. The other one, second type, are, for example, the modular relations between some standard functions. Let me give me an example, like the theta series here, and we have it's a modular form of weight 1/2 with certain multiplier. This is a pretext to introduce notations. So E of z, excuse me, I should use here. Yeah, E of z is e to pi 2 pi I z. That's the standard additive character on real numbers. And the modular relation, like for theta series, can be derived by applying Poisson's formula. Here is the one. The sum over, we have a distant test function f, summation over all integers is equal of values of f is equal to the sum over the set of integers of Fourier transform of values of values of Fourier transform. This is the Poisson summation formula that can be used, for example, to prove the modularity of the theta series. There are, of course, other ways of doing things. And classical number theory employs Poisson summation quite effectively. Also, it's in its generalized form in many variables, but usually for abelian groups. And I don't mean this just apply like as it is. There are many ingenious tricks to proceed, but there's no room here to talk about that. It's just the idea behind of identities of the type is the Poisson summation. But that is, I would say, the borderline of the classical number theory. Today, modern number theory applies powerful tools from, it's powered by transformation formulas of different type, of trace type, which are derived from harmonic analysis on non-abelian groups. And I will mention today a few of them, like Peterson, Selberg, Kuznetsov, and variations on these. And also I will try to give some consequences, applications. By no means I can exhaust the subject in 1 hour or less, so it will be really not representative. I just pick up a few that came to my mind when I was preparing the transparencies. So let me start presenting the spectral theory first. As I said, most of our interest goes to the congruence groups because of arithmetic. Even the Hecker congruence group would be quite sufficient for us. It's a Hecker congruence group of level Q. However, to understand the subject from better perspective, I think it's good to start talking about any function group acting discontinuously on the upper half plane, which is cofinite, has a finite co-volume. Such groups, such generality may be useful to understand special cases, the arithmetic cases, because we can appreciate the wealth of special features for arithmetic groups. Otherwise, we could just take it granted and forget how beautiful is the case of congruence groups. And also the advantage of congruence groups or arithmetic groups in more general, slightly more general, is that you can view them in representations in adelic setting, for example. Also, there's a very rich theory of Hecke operators, which absolutely, it's not only good for arithmetical, for algebraic investigations, but also helps very much to get good results of analytic type. And particularly, I have in mind here the amplification technique that really requires forms to be Hecke forms, etc. I will not probably talk about this at all, and I don't want to postpone anything for Bill's lecture, so maybe missed just that. But I just wanted to say so. And the generality is also very interesting. The Lagrange program, which we now celebrate during this conference, does not really apply in that generality for arbitrary groups. And soon you see certain features that there's no room for arithmetic in some of the investigations. Yeah. Okay, so the spectral theory on upper half plane, I will not be completely general, but relatively so. So let f be a function on upper half plane, complex valued, and k be a real number, which we call weight. And if f transforms according to this rule here, you know, where theta is called multiplier of absolute value 1, and f has some polynomial growth at cusp, whatever it means, I will explain maybe a bit more precisely later, then f is called automorphic function. So it's a kind of generalization of some kind of gamma periodic function with some multiplier system in it. And when k is, for example, integer, then theta is just the multiplication is just a character of the group. And if k is half of odd integer, and gamma is a congruence group, then theta is essentially the Jacobi symbol times the Dirichlet character modulo q. There are some variations of Dedekind sums and things, but the bottom line of that is really Jacobi symbol. What is behind the things. So you just get a feeling what multiplier system could be. And those cases, integral weight and half integral weight, are both very important for number theory. Example of, okay, I said what automorphic function was. It's just a kind of gamma periodic function. By automorphic form, I mean some regularity condition is imposed on it. Not necessarily holomorphy, but it has to satisfy some PDE equation, and then I call it automorphic form. And this is given by, this has to be an eigenfunction of suitable Laplacian. The Laplace operator of weight k is given here in xy coordinates this way, and we ask f to be eigenfunction of that operator with lambda to eigenvalue, a complex number. Typically, we just parameterize the spectrum in this way. Lambda is s times 1 minus s, and we also think of s as being 1/2 plus it. Don't get it wrong. This is not necessarily on the critical line. It's just notation. So t itself could be a complex number. So of course, this is a double cover complex plane. I mean, s times 1 minus s, except for 1/4 point. But that's a minor issue. So automorphic form, in addition to be automorphic function, has to be eigenfunction of the Laplace operators, which is some kind of generalization of Cauchy-Riemann equation for holomorphic forms. It's a very strong property. An example of being eigenfunction is automatically real analytic, for example. Yeah, the basic example, most important for the theory, are the Eitan series. I've been troubled to define them completely, but I'll give you some hint how they are, how we proceed with it. Suppose gamma has parabolic elements. So Eitan series do not exist for compact groups or those which do not have parabolic elements. A fixed point of parabolic element is then a cusp can be viewed as a cusp in this picture of fundamental domain, and it's a real number at infinity, and let gamma sub a be the stability group of the cusp. If the multiplier system is trivial on the stability group, then we call a singular cusp. of course, with respect to this multiplier system. And only for singular cusp we can define Eisenhower series. For every and each one singular cusp, we define Eisenhower series. E sub A of Zs. Z is the upper half plane variable, and S is a complex parameter, the spectral parameter. And let me just define that fully. That will be just time consuming. Let me just give you an example. When A is a cusp at infinity, and the stability group is just a group of translations by integers, which we can always do by conjugation the group. Then the Eisenhower series at this cusp is given in this familiar way as infinite series over the cosets, gamma modulo of stability from the left, and the imaginary part of gamma z to s, etc., etc. And this series converges absolutely for real part of s larger than 1. And is easily seen to be automorphic form. The modularity is clear because of the constructions of arranging over the group, and the fact that it's eigenfunction of Laplace operator is clear because the term-wise we get elementary functions that do satisfy eigenfunction equation. I found it very mysterious, amazing when I was studying first time automorphic forms in their generality, that one can establish meromorphic continuation of such a BIST. I mean, we know nothing about the group gamma, and so Selberg and Langlands in larger generality did succeed to prove the meromorphic continuation of the Eisenhower series for to the whole complex S plane. I don't know if you have to probably take my word granted, but try yourself to prove without knowledge of what's in the literature. You see, you don't even have a starting point for doing something like that. Now, if it's congruence group, you have the matrix entries A, B, C, D are integers. Now you know how to sum integers, use Poisson summation here, there, manipulate, take use of 10 fingers, and maybe if you're lucky, you can get something. But if it's just abstract group, acting discontinuously on upper half plane, there is no room for such investigations. You have to do something more clever, and I have no room neither here to talk about this. Nevertheless, I am still fascinated that such things are really established in such a generality. More to the point, the Eisenhower series does satisfy one of the standard functional equations, which could be viewed as analog of Poisson summation. So all of a sudden you have an abstract group and you have kind of Poisson summation involved. That's not so simple though, because the Eisenhower series has to be taken as a vector. You have to take the collection of all the Eisenhower series for each singular cusp in it, take the column vector Eisenhower series, and then it satisfies matrix functional equation or vector function equation where the factor in front of the Eisenhower series is called the scattering matrix. And you can identify these elements of the matrix by expanding the Eisenhower series into Fourier series. For every pair of singular cusp A and B, you have Eisenhower series associated with cusp A, and you expand this at cusp B, and the expansion is of that type. It's just the constant terms are very simple, y to s times y to 1 minus s, or the zero term, I prefer to say so. And phi, the coefficient in front of y to minus s, is called is the important function, the element of our scattering matrix. And the other terms involve Whittaker function, the non-zero terms. In the critical strip, that means when S is between, a real part of S is between 0 and 1, the poles of Eisenhower series are exactly the poles of the scattering matrix, and they are all are simple, and they are in the segment 1/2 to 1, excluding 1/2, I emphasize strongly that, or in the strip to the left of the critical line, real part of S 1/2. That's the theory, a beautiful theory, and in such generality, it's amazing. This, in particular, there are no poles on the critical line. Vital for the spectral theory, because they will give you continuous spectrum. Okay, what about the structure of the space? We gave examples, the Eitan series, and the other important concepts. I mean concepts and mass-cast forms. These are essentially guys orthogonal to the space spanned by Eitan series. Whatever definition you take, the result is that an automorphic form which vanishes at every cusp is called cusp form. They are not compactly supported, but they have such exponential decay at infinity that they behave like compactly supported. That's why you probably wouldn't be surprised that the spectrum of Laplace in that subspace is purely a point spectrum, because they behave, even though they are not, like compactly supported functions. And oh, yeah. Okay. Thanks, Jim. Yeah, well, read infinity is 0. Yeah, I have no. I know, I do have, yeah. Okay. Cap 0. Yeah. Okay. And we call this, so there are no constant terms here. In the Fourier expansion, you just have all the Whittaker functions, and the coefficients in front of these are called Fourier coefficients of the cusp form. Yeah. Spectral theorem, quickly. Let L square of gamma be the space of automorphic functions, I mean, of weight k, and square integrable with respect to the inner product. This is natural inner product in that space of automorphic functions, and d of mu z denotes its invariant measure on the upper half plane. And C sub k of gamma is clearly a linear subspace of, and the space of cusp forms, the linear subspace of the linear subspace spanned by cusp forms is a subspace of L2, and also there are a finite number of residues of the Eitan series at the poles located on the segment 1/2, 1. Only those matter here. And let R sub k of gamma denote the subspace, linear subspace spanned by the residues of the Eitan series. It's a finite dimensional subspace, of course, because they're analytic, and the poles come from a phi of S. Phi is a meromorphic function. There cannot be infinitely many poles on a segment, on a compact domain. And these are orthogonal subspaces, and the Laplace operator is self-adjoint and acts on these subspaces for a very easy reason. You can see it. And the theorem says that it has purely point spectrum in those. And it covers a segment from k-half, 1 minus k-half to infinity. It's included in that section. So the bottom of the spectrum is k-half, 1 minus k-half. And the orthogonal complement to that subspace, which can be very nicely characterized by incomplete Eitan series. That's the way actually one should really start the theory. But anyway, we are reversing the presentation. So the complement, orthogonal complement to that subspace, the Laplace operator in that subspace has purely continuous spectrum, which covers the segment uniformly from 1/4 to infinity, with multiplicity equal to the number of inequivalent singular cusps. So if there are no cusps, for example, there are no continuous spectrum, the whole thing is much simpler. Yeah, like with the example being hyperbolic groups that are groups for quaternion algebras, etc. But we are interested in cusp because of Fourier analysis, and we are interested in Fourier coefficients. So cusp are really very welcome in the picture. And the theorem says that the continuous spectrum, the eigenpacket of continuous spectrum, is formed by the vector Eitan series on the critical line. That's where this is the unitary. And the spectral measure is just 1/4 pi times dt for this. So that's the spectral theorem in such a generality. here one should realize that it does cover that theory, classical situation when that means the classical, that means holomorphic cusp forms, they really lie at the very bottom of the spectrum. And I emphasize, I'll make a point in a moment out of it. Precisely if F is a cusp form for group gamma of weight k, and it has then Laplace eigenvalue. Let me assume k is non-negative. I just don't want to talk in negative terms. And the Laplace eigenvalue is exactly k half, 1 minus k half, which is exactly the bottom of the spectrum, as I said before. Then the function f multiplied by power of y is holomorphic. I mean, if and only if it's a holomorphic modular form or cusp form for gamma, for group gamma. So it transforms in that way as it is here, and it vanishes at cusps. So you see, you have a larger picture what these classical automorphic forms, where they are located in the whole theory. The eigenspaces are finite dimensional, and actually there's no much benefit of considering k, every k, as far as mass forms are concerned, because there's an isomorphism between eigenspaces ck and ck plus 2 on the level of eigenspaces, if provided the spectral parameter s is not real, or is not a half integer properly, because, and this isomorphism is given by simple linear differential operator due to mass. So you can always, go from k to k plus 2 or back. So there's no much interest. However, there's a big interest for holomorphic forms of different k's. They are re-emerged or are annihilated, depends which way you go, by these operators k and lambda of mass. Yeah. Well, I just for your pleasure wrote this one example of such operators. Okay, here's a theory. Eisenhower series cusp forms in the residue of Eisenhower series. And do they exist? Eisenhower series do exist. We constructed them. See, but what about cusp forms? It is very frustrating even today to tell that even for the full molar group, the simplest possible case of weight 0, we don't even know any construction of a cusp form. We know the existence by a roundabout technique using Selberg trace formula, counting the spectral. It's a very large subspace, but no one ever succeeded to construct a single cusp form. Oof, like that. So the question existed long ago, but was pretty much ignored in a way, because I think people thought that they do exist always because of the trace formula and congruence groups. So do mass cusp form exist? The first question. How large are the eigenspaces? I mean, multiplicity, for example. And there will be issue of small eigenvalues in applications. I mean, of Laplacian, and the question would be how many are there? Of course, as Shahidi mentioned about Ramanujan conjecture, that they are really related to Ramanujan conjecture, analog of Ramanujan conjecture for infinite place, so to speak. But somehow, for analytic purpose, I'm not making. I differentiate these objects somehow, even though they are really unified in the representation theory by very beautiful treatment there. Okay. In order to address the first question, do mass cusp form exist? Let me first formulate the Selberg trace formula, because many things come from it. Let's for simplicity assume that k is 0, the weight is 0, and the multiplier is trivial. The point spectrum is just covered from 0 to infinity. The spectral parameters Sj can be viewed in the S-plane this way. S0 equal to 1 always belongs to the spectrum. The constant function is there. And we have here a critical line, 1/2. Many of these points Sj are supposed to be on the critical line. but there could be some exceptional, those who are between 1/2 and 1. Let's take a test function, holomorphic test function h of t, which has a special, which is holomorphic in horizontal line segment strip, and it's even and satisfies some growth conditions or decay conditions. Then, having such a function, the trace formula gives you a relation between the average over the spectrum of the function h. The point spectrum is accounted here on the first summation. The continuous spectrum is accounted by integral here. I'll explain in a moment what phi is. And the right-hand side contains a contribution of the conjugacy classes of the identity, which is the main term in the formula. It's a certain integral times the volume of the quotient space. Then sum over the parabolic, over hyperbolic conjugacy classes, call it P, and capital P is called norm of the class, which geometrically means that log of P is the length of closed geodesics, corresponding closed geodesics. And we have other terms coming from elliptic elements and parabolic, so to speak. They are not important for today, so I just put dots over there. Phi of s is the determinant of the scattering matrix, and g of x is just a very simple Fourier transform of the test function h. So that's what trace formula is. It connects spectrum with, quantities with geometrical invariants, the length of geodesics, etc., etc. It's in the simplest variant, of course, of the trace formula. Probably I have more prepared in my notes than on transparency, so I closed the notes. I worried I missed something good, so let me just go back to it. Yeah. No, not really, not yet. Yeah, okay, yeah. Okay, so one of the main consequences of the trace formula is the Weil law for the spectrum. I mean, it's a asymptotic formula for the number of the spectra. How we measure that? I mean, this is typical in number theory that you want to prove existence of something by just counting, and if you succeed to get asymptotic formula that is non-zero main term, you prove existence of the object that you're counting on the left-hand side. So this is the way you can prove existence of cusp-forms or whatever other things by just establishing asymptotic formula for the total spectrum. So Weil law is known in many environments. Here, in the case of the discontinuous group, it reads in the following way. So n sub gamma of t is the number of eigenvalues of this eigenvalues parameters tj of height up to t, and the trace formula will tell you that number of them is at most t square, quantitative multiplicity. How we account the continuous spectrum? It's a continuous spectrum is accounted by a corresponding integral with logarithmic derivative of the determinant of the scattering matrix on the critical line. And again, the trace formula will tell you this is less than or equal to t squared, I mean up to the constant. More precisely, the total quantity that we are measuring, the point spectrum plus continuous spectrum, is asymptotically equal to t squared times the volume over 4 pi. And there are some more precise results there. Perhaps you should also realize that m sub gamma of t, a quite mysterious object which accounts for the continuous spectrum, really is counting the number of poles of the Eisenhower series to the left of the critical line of the height up to t and up to the error of O of t. So it is, again, some kind of counting function. Yeah, and that's what Selberg established. This is all Selberg, there. Well, since the formula contains both point and continuous spectrum, the total here, you still can't tell which one is larger, if any. We are lucky that for congruence groups, the scattering metrics are given by L functions of number fields, and these are the functions of order 1. We can easily count the number of poles, things, and it happens the continuous spectrum contribute no more than t log t. Since the total quantity is of order of t squared, voila, we are happy that we have asymptotic formula for the number of point spectra but that's for congruence groups. It's about T squared of order times the volume. See, hence, there are infinitely many cusp forms, plenty of them. And again, repeat myself, even for my group, nobody even constructed a single one. You know, the power of counting here. All right. Okay. Having that situation, one can be foolish to think that there should be general. I mean, that lots of cusp forms should be there, rather, and the Eitan series should contribute very little. And in fact, there was a silent conjecture by Selberg of that type. But about now 2 decades ago, Phillips and Sarnak developed a whole theory of deformation theory and could provide evidence just against that. It will show us how that congruence groups are very, very lucky and very good, very rich. I mean, they do have plenty of cusp forms. Well, I say lucky because I do like cusp forms, you know. Of course, you may say unlucky because, okay, you see in a moment what I say about this deformation theory. So, I mean, there's a difficulty to separate continuous and point spectra by trace formula. I mean, you may think you just take a test function which is located on point spectrum and go away from continuous spectrum. No way. Such a function would not be good enough to get any benefit from the other side of the trace formula. So it's like uncertainty principle of harmonic analysis. If you shrink the support of a function, its Fourier transform expands, and so you have to, and vice versa. So you have to make a good balance for test function to get the best use of the formula. And life shows that in the trace formula, you cannot do it by test function to separate continuous and point spectrum just by playing with test functions. So here is something really interesting. Let them U sub j of z be a mass cusp form of weight 0 for the gamma 0 cube group and eigenvalue lambda j. And it's necessary to assume there are also Hecke eigenforms. I'm sorry I have no time to define Hecke operators, but these are just arithmetically defined operators which brings a lot of arithmetic into the structure. And for such a cusp form, mass cusp form, we introduce a Selberg-Rankin-Selberg L function, zeta function, or L function, where A and are Fourier coefficients of some fixed form, holomorphic forms of weight 4. Okay, so these are the definitions. Well, I should probably reveal first the intention. The Phillips-Sarnak theory was intended to disprove that there are so many cusp forms. So in order that means you have to look for groups that are not congruence groups, definitely, and how you can find them is very difficult. But there are general procedures. You can deform the group and try to chase the cusp form with your deformation parameter and see where it is going. That's what actually they didn't deform the group, they deformed the metric, preserving the constant negative curvature, and then by uniformization theorem you have a group, in other words. So the result of this is that if the L function of Rankin-Selberg at this very special point, Sj, does not vanish, then the cusp form Jz can be destroyed. So where it goes, I mean, it goes very reluctantly, by the way. If you make a graphic, you know, there's a tangent line, you know, to the critical line before it leaves, you know, to the left and becomes a pole of Eitan series. That's the only room that is left for cusp form to disappear. So that's the way of trying to find examples of groups that have no cusp forms or very little of them. So the problem reduces now to a very arithmetical one, as we can see in other lectures, I guess, you know, to the question of whether a function of a very arithmetical meaning, Rankin-Selberg function for these automorphic forms, does not vanish at this special point. So the non-vanishing of L function at special point is a hot subject today. I mean, elliptic curves, the conjecture, and other things. Here is an example when non-vanishing of a special point means so much for us. And so Desi and myself, long time ago, being commissioned by Pierre, proved that there are infinitely many, clasp for which this central value, the special value doesn't vanish. And recently, Lou established positive density of those do not vanish. So you can destroy a positive density of clasp forms. As a result, the very low collapses doesn't work anymore. And there is even an expectation that there are groups for which the cuspidal spectrum is just bounded and then finite. So bad, for this. For me, it is interesting here is that it offers, it gives you, produces a zeta function, which is very natural. Zeta function, the scattering matrix, it's given by Dirichlet series, which is meromorphic of order 2. Very unusual. A function which is meromorphic, of course there's no Euler product there. Meromorphic of order 2. And it satisfies one of those standard functional equations. Think of this. This is something really puzzling. Yeah. Okay. Let me control my time. Other quick consequence of trace formula is the closed geodesic theorem. You can apply test functions in the reversed order and count the length of geodesics rather than spectra, and you get something like which is analogous to prime number theorem. The main term is x. There is some contribution of small eigenvalues. That means this exceptional between 1/2 and 1, the spectral parameters, and the error term is x to 3/4. That's a standard result. It's due to Selberg, unpublished, obviously. The Riemann hypothesis is true for the Selberg zeta function in this case. I mean, Sj is a 1/2 plus it. Let's think about the model group. So each and every term here is of order x to 1/2. However, there are so many of these eigenvalues that you can't estimate this by x to 1/2 as expected, because there could be some cancellation in sums of this kind. So for the congruence group, it was succeeded first by myself in some years ago, but then put to the state-of-the-art technique by Liu and Sarnak, and they got error term x to 710. Well, it's less than 3/4, but the point is really not that. The point is that they succeeded to prove cancellation of terms x to sj. So somehow of distribution of eigenvalues on the critical line is needed. And another point is that it uses arithmetic quite heavily. There's certain estimates, very good estimates for Rankine-Selberg functions, etc., etc. And I think here also uses the new bound for the small eigenvalue, right? Yeah, that requires higher rank functions. I think we have to be careful about time, so let me skip the issue of small eigenvalues completely. You had already time to read this, yeah? Yeah, so just Selberg conjecture. Well, I take excuse because Friedrich Shahidi mentioned that already, and this is the famous result 7/64 with Kim, etc. So let me skip these things completely. Maybe I should also skip the problem of multiplicity of spectra. It's a fascinating problem. We expect, for example, that for the Fulmler group, the spectrum is simple. I mean, the eigenspaces are one-dimensional. That's probably a problem for the next millennium, I guess, I would say. Yeah. Okay. But have a little intuition. If group is gamma 0 q of level q, and then the dimension of holomorphic guys, those are at the bottom of the spectrum, is of order k times q. Just have this in mind. I want to make a point. The fact that dimension of holomorphic forms is as large as k times q, where k is at least larger than 2, can be easily understood from the spectral analysis because these eigenvalues are isolated in the spectrum. So even playing with test function, you can pretty well treat the whole space being away from the other guys. You can, of course, use also geometric arguments in this case because of the special structures there. However, what about k equal to 1? Extremely important case, the weight 1 guys, then the bottom of the spectrum is exactly 1/4, and that's where holomorphic forms are living on, and also where is the bottom of the continuous spectrum. So everything collapses there. There is no way of playing with just test function to separate the contribution of Eisenstein series and maybe other mass forms from the holomorphic ones. So the question is, how large is the space of holomorphic cast forms? Trivial bound would be just about the volume of the group, which is about Q. But we do have some help from arithmetic. There are very precise characterization of those guys. Deligne and Serre, 74, proved the following theorem, that every cast form of weight 1 for the character chi comes from irreducible two-dimensional representation of some number field extension L over Q. And this way we have instantly classification of such cast forms into dihedral, tetrahedral, octahedral, and icosahedral, depending on the image of rho in the GL2C. So we can talk about Hecke forms of that type. And suppose for simplicity that Q, the level of the group, is actually a prime number congruent to 3 mod 4, and chi is the Legendre symbol. So yeah, the parity is here guaranteed because of P is congruent to 3 mod 4. Let K be the imaginary quadratic field of discriminant minus P, or the ring of integers, the class group, and the class number is there. If you take a class group character psi other than 1, it's complex because P is prime number from the genius theory. There is no other genius characters there at all. We define the function, the kind of theta function, which is a cast form of weight 1 for the group. So we have, and we have relations with the psi and psi bar, the complex conjugations taken, you get the same cast form, but there are no other relations. So the dimension of the space of weight 1 forms is at least h minus 1 over 2. And by Ziegler bound for the class number, it's P2.5 minus epsilon. But it's far less than the volume of the group, which is about P. Serre conjecture that most of the guys in the space come from this dihedral. Yeah, I should say those correspond to the dihedral representations. The other guys of dihedral and the icosahedral, I think that in this case there are no tetrahedral guys, is O of P to epsilon. And that would be a very, very strong result, but we are far away from proving the things. However, given the fact that the volume is about P, it is extremely surprising result, I would say, of William Duke, that he established that the dimension of the space is less than P to 11 over 12. Have in mind this naive approach from trace formula using test functions that will give you only P. So he had to do something good about how to isolate this icosahedral and octahedral forms from the rest of the spectrum. And indeed, he did it in the following manner. There's a conflicting properties of these special representations. They are non-dihedral ones. On one side of the picture, we have orthogonality, the large-sieve type inequalities for the Fourier coefficients, which it's expressed in terms of such inequality. if B is just a basis of all these forms, we have this bound. Actually, I should emphasize this is not so easy to prove, because we are talking about weight 1, and nothing like Peterson formula applies. You have to use duality to prove it, but Bill succeeded to do so. So that's one thing, but this is inequality for any complex numbers an. So if this is so strong, just take my word, it is, you have no time to digest, you know, then there must be some huge variation in the argument of lambda f of n. Well, if you take this, let's say, the octahedral guys, the set of values at square of prime is bounded, it's 0 plus minus 1 or 3. So you can see this is conflicting with orthogonality unless the number of such guys is very small. Okay, that's how he proved. So this is provided by Sayag, and then the proof is that the octahedral subspace is P278, and then icosahedral is 1112. So this is the wonderful example when analytic methods and some arithmetical characterizations play nicely. Yeah, there's my clock again. I lost my clock. It's here. Yes. Okay. In number theory, when we start, when we want to study cusp forms, whether in level aspect or spectral aspect, integer cusp forms, the great idea goes by extending this to a family of form. It's interesting that dealing with bigger objects like families, average over the family, gives you a better picture than treating the individual terms directly. And then having some parameters like Hecke operators, twists, etc., we can recover from average results for individual forms. That's what is in the essence of the amplification technique. I'm not sure if you will have time, as I'm running out of time myself, so you probably will too, to describe these in details. But that's the concept. Yeah. So in order to deal with average over spectrum, we need trace formulas. And so Selberg trace formula is one of type. There's other one of Peterson, which involves Fourier coefficients of cusp forms on one side, rather than just test function. And there is a different normalization factor here, omega f, which is defined here. And on the other side are the Klosterman sums and Bessel functions. Sorry, I have to rush. So so this is Peterson formula, classical one for holomorphic forms, and there's analogous formulas for mass forms by Kuznetsov. Advantage of that is that it contains spectral parameters that are continuous. You can play in the other direction and establish spectral resolution of sums of Klosterman sums rather than treating the Fourier coefficients. So if S is such a sum of Klosterman sums, F is a test function, then the Kuznetsov formula looks like this. Oof, like this. There are Bessel functions, transforms, etc. Okay? Yeah. And this is a right way of writing Klosterman sums in terms of the spectrum, because these are just adequate harmonic to study the beast. So Peter Sarnak and Liu and Rudnik, using powerful tools from what we know from automorphic forms of higher rank, that means the estimation of small eigenvalues comes into it, succeed to prove this bound, x to 5th. The trivial bound is x to 1/2. The key point is that it does it shows the cancellation in sums of Klosterman sums. There is a variation in the argument of Klosterman sums gives you cancellation, and this is really due to the fact there are no small eigenvalues. Laplace operators, and the fact that you have 2/5 rather than trivial 1/2 is vital. Yeah, the cancellation Glasman sums is because of the progress over the Selberg bound for small eigenvalue 316. So 1/5 would be okay, but we have even better today. Yeah. It's still an open question about how Glasman sums arguments vary when the modulus is prime number. And here's a famous conjecture of Katz that the angles of, yes? Right, you said that, right? This is your conjecture. Right. Well, I said so, yeah. So the angles of Klosterman sums are equidistributed, but not with respect to the Lebesgue measure, but a Sato-Tate measure here, which is very much a GL2 type measure. It also appears in the context of coefficients of transforms. Yeah, I mentioned these two trace formulas, Selberg trace formula and then Peterson-Kuznetsov type formula. They are very different in nature. On one side, we have spectrum, but purely counted by test functions in trace formula, and with certain weights of arithmetical type in the case of Peterson formula. And the benefit of the other one is that we get Klosterman sums rather than closed geodesics, which are more accessible objects. We can use algebraic geometry to estimate and other things, while closed geodesics still remains Schrödinger mystery. But as we study for algebraic reasons, so there is a problem of normalization of forms, how to come from one formula to other, so it boils down to, we have two types of normalization. Either we can set for Hecke forms that first coefficient is 1, or we can say analytically or spectral normalization that the L2 norm is 1. And you would like to know, in quantitative terms, how the change of normalization affects your estimates. Computing residue of the Selberg function, you can find that if you assume the normalization is the first one, the arithmetical one, then the inner product is essentially the value of the symmetric square function at point 1, the one that Franz mentioned this morning. And so the problem boils down to estimation of the symmetric square function at point 1. And you are familiar with Analytic number theory, the lower bound is very difficult because it really sounds like a Ziegler zero problem for L functions. And so Lockhart and Hofstein succeeded to prove a lower bound, very good one, effective. The upper bound is rather easy to get by proving that there are no exceptional zeros for symmetric square functions. It's very, very astonishing because symmetric square functions are much harder than Dirichlet functions, and here we have better results than for Dirichlet functions. See, and here's a wonderful example how, as I said at the very beginning, one can use indirectly the theory of higher rank automorphic forms for the benefit of the GL2. That means that it's just improving working conditions in GL2. So I don't claim there are no use of higher rank. I said there's no direct applications to problems in the number theory, but the use is tremendous. There is a great potential there, and here is a wonderful example how this could be used. You know, now we have no problem with normalization as far as the order of magnitude of the normalization factors are concerned. See, so I have no. I mean, they use not only the symmetric square function, but they used also modularity of other functions to combine using Landau-Ziegler ideas. So they really had to use modularity of L functions, I think of degree 6, maybe, or 4 or 6, something like that. Yeah, yeah. So there is such use, indirect, a powerful use. Well, so far I didn't see any application whatsoever. There is zillions of them. So I have chosen one to wrap up. And what I said at the very beginning, we had identities of combinatorial type and identities of analytic type with a trace formulas. I mean, harmonic analysis is there. You see, and that's why I have chosen an example concerning prime numbers, because. Okay, so the problem is this. You have a polynomial, quadratic polynomial, which is irreducible over integers. And we ask a question about how the roots are distributed when the modulus P varies. There are two or zero roots. But if P varies, we may have a lot of solutions. So, the result that really employs whole machinery of spectral theory of automorphic forms and other things is that these roots are equidistributed. Precisely, Duke, myself, and Rapatot proved that result here. That what means equidistribution, modulo 1 of the roots of the fractions nu over p. You see so you can understand probably vaguely that modular forms are related because roots of quadratic congruences can be linked to some Poincare series, can be controlled by Poincare series, and then use spectral theory to study that Poincare series. But how do we get prime numbers here? There are no prime numbers in GL2 theory anywhere where except function. So here is the sieve part. Sieve theory allows you to partition the object into pieces. One pieces can be treated by one kind of harmonic analysis, the other pieces by a completely different one. You see, so this marriage of combinatorics and harmonic analysis is fruitful, and this is one of many examples. Thank you.
Do we have any comments or questions?
Yes. No, I think you have now result with Kim better than they had at that time, and you can beat them. Peter, you know? There's the 2/5. Oh, yeah. Yeah, if you take a smooth sum rather than sharp cut at x, the modulus, then of course you get x to epsilon. Yeah, I'm glad you asked about Klosterman sums, because I forgot to say that why we're making a great deal of Klosterman sums here, because they are on the way of proving many things in number theory. They are instrumental, and that's the way originally automorphic forms sneak into number theory, through the estimates for Klosterman sums. I mean, those are better estimates than for individual from Weil and from Riemann hypothesis for K, something like that.
Any more comments, questions?